Continuing on with our value noise 3D implementation, here in part 2, Lee's going to, I guess you can say, get the core functionality set up now.
Yep, we're going to actually take our value noise 2D and duplicate it and repurpose it and add the functionality we need to make it work as a 3D. Saves us some coding. And the principles are the same. We're just doing it in an extra dimension. So we need to add in our z dimension, which means we're going to need a variable for holding its floor. So that's going to be var k equals floor of z, or z. And then we're going to need some additional values here for holding our low and high values of z. So duplicate those. So z low is going to be equal to k. And z high is going to be equal to k plus 1. And we're going to need to do 4 additional smooth noise lookups. So not only did we effectively double our smooth noises, because if you remember before we were doing 9 lookups on smooth noise, we've then doubled the number of corners and the number of sides. So now we're up to 17 lookups, so almost double what we were doing before inside of the smooth noise. But on top of that, we're doubling the number of lookups for that. So you can see why I shaved off those extra 8 sample points on the unit cube for the sides, just trying to save a little bit of space here and there. All right, now we're going to have to rename these because we're dealing with the z as well. So we're going to have NLLL.
Great names.
Well, in mine it's N000, but I didn't want to confuse people with binary on top of everything else. So we'll rename that. Then NHL, L, not the National Hockey League. NLHL. Then HHL. So that takes care of those. Now these are going to be the same, but the Z parts are going to be their high counterparts. Then here will be ZL. For the first 4. The second 4 will be HL, or sorry, ZH. They get confusing. And this is still easy. We haven't gotten into Perlin and Simplex yet. All right, so those are our samples. Now, just like we sampled our fractional component of x and our fractional component of y, we need a fractional component of z. So this will be var w equals z minus k. And where we have more fun, here we go. Where we had 2 lerps before, we now need 4. So we need to deal with the first 2 being what am I trying to think? So we've got our lows here and our lows it was z. So we've got low in x and for let me re-say this. We've got our lows of y, our highs of y, and we're going to have to deal with our conditions with our h's being, or z's being low and then our z's being high. So the second 4, instead of z being 4, we need to do z's at their high variations. And then we need a different denominator here. So these will be ny and then low and low. So this will be low and this will be low. And these will be NYLH and NYHH. So we need to duplicate these. So this will be XY low and XYH. So then we need to take the H versions here. And we're still not done, because now we need our NXYZ, which will be the lerp of NXYL by NXYH, and this will be by an amount W. And we return this variation. Now, what we're doing is we're just like in the 2D where we were taking, and actually we still have the Photoshop part of it.
We do.
Oh, yeah. So that one's this one. Nope. This one?
Yes.
There. Okay, so just like before, we were taking U and V and all of our corners and figuring out our contribution at this point. We have to do the same thing at the bottom of the cube, the top of the cube, and then we have to figure out in the center, because now this is a three-dimensional space as opposed to a 2D. So what the code is doing is this part, that didn't work kind of the way I wanted it to.
Whoa, hang on.
Yep, I got that in there again. All right. So this part of the code and this part of the code are calculating the information on the bottom part of the cube, where these two lines of code and this are calculating the contribution at the top face of the cube. So if you look at it as two of those cubes stacked on, or squares, stacked on top of each other, one's calculating the contribution at the bottom, one is calculating the contribution at the top. This one is calculating the contribution halfway between, or the W fractional part between the bottom and the top squares, and getting that third dimensional sample. And then we're adjusting it for -1 to +1. So lots and lots of samples, lots of lerping, and you could also do smooth step or any of the other interpolation techniques that we discussed with the 2D. All of those should still work. If I build that out, no errors there. Now, we're still set up to use noise smooth noise, but what I want to use is value here. So now instead of using the smooth noise part of it, we're going to sample our real noise method. So if we go back, and actually before I do that, let me take this and raise it up a bit, because I'm not sure how long it's going to take to run one iteration. So if we go back to here and hit play, so 9 seconds. per iteration. And then we've got the black going on again. So if I pause that and we go back to our code, and that would be because I didn't do our resampling, because I'm returning a number that is in the -1 to 1 domain. So I need to go ahead and add 1 divide by 2f. That will put us in the 0 to 1 domain. I'm also going to go and take our texture size down a little bit lower for this one, just to speed it up and see what kind of response time I get. Because what I'm trying to get to is to be able to show the animation on it. And with larger samples, we're not going to be able to do that. All right, but we get, a worse looking image. But it is uniform in gray, no black overall. So now, if I take this, I forgot to check the sample time.
No, put it down to 0.7.
0.7?
Mm-hmm.
Okay. And I can probably take our iterations, because now that we're using our noise as opposed to, or value noise as opposed to smooth noise, I can use fractional.
Do you still want to go back up to your value noise?
Uh-huh.
Go ahead. Do you still want to cast that to an integer, your iteration now?
Oh, yeah, you're right. Good catch. Yeah, we actually want a fractional iteration, otherwise we won't see anything. All right, so now if we run this, so now we start seeing our noise morph from state to state.
Very cool.
As opposed to, and actually we can go even lower. We're at half of a second here. So we can go down to about 0.6 and still be fine. And I'm going to take that down to, say, 0.25. And I'll drop this down to 16. What I want to try to do is get this running as fast as I can.
Mm-hmm.
Even if the sample size is a lot smaller and rough looking, but it can show
The smooth.
the animation. So I don't know. I'm getting lag on my side, so I don't know how smooth it looks.
Yeah, it looks really smooth.
So it should be shifting really smooth from state to state,
Mm-hmm.
which is what the whole point of noise, or of value noise and the Perlin noise and the simplex noise, is so we can get a noise that we can animate and have it, instead of looking like white noise on a TV where it's just completely random, we want it to look like it's shifting. This comes in handy for things, say noise on a camera. If you wanted to animate some jitter, you don't want it jumping all over the place randomly. You want it to have a smooth transition from state to, or position to position. If you wanted to do something, say like clouds, we could do some math magic so it wasn't solid or a uniform gray similar to this, but we had a lot of empty areas. But then we could use a higher resolution noise than what we've got here at 16 by 16, and then say every 10 or 15 seconds we could shift the noise by the next iterative process, and then it looks like we've got clouds that would be changing in shape from moment to moment gradually, as opposed to just, wow, 1 second there's a cloud there, and then the next second there's no cloud, but there's a cloud over there instead.
Right.
So, but that's the whole point of getting into this stuff. Now, what we need to do after, or in the next video, is start looking at something that's a little bit faster than our value noise. Value noise is cool, and it's definitely got its uses. But as you can see, unless you want something that is only a few pixels across, it's not something that we're going to be running in real time.
Right.
So,
Do you use value noise at all in any of the other R&D stuff that you've done so far?
I have, and because it is one of the simpler noises to mess with, it was the noise that I started playing around with to generate my world inside of the Minecraft-like game. So that was the basis of the noise I was using for generating that world, but it was incredibly slow. And I was under the impression when I first read it that value noise was Perlin noise, and that was my mistake. And I had learned after the fact that it wasn't, which is one of the reasons why I wanted to um, mess around with Perlin noise and re-implement that particular terrain generator.
Mm-hmm.
So it's like I said, if you want something simple that works and you're not worried about the time it takes to generate stuff, then it's a good noise to mess with. But if you want something faster, we need to start looking at either the Perlin or the Simplex.
Okay, very cool. So this is going to conclude the value noise altogether, right? And we get to move
Um,
into
Perlin, yep,
Perlin?
yep.
Fantastic. All right, well, with that, that is going to wrap up this video. Thanks a lot, everyone.